This is my third lecture in the series of the lectures of Digital Signals Processing Made Easy. Today I will discuss the discrete systems and the types of the discrete systems and the foundation of the DSP. The techniques on which almost all of the DSP is based, that is decomposition and the synthesis, that I will discuss in this lecture. So in my third lecture, let's start with the discrete time systems. What is discrete time system? It is a system that processes an input sequence xn to generate an output sequence yn with more desirable properties. So the input of this system will be discrete and the output of this system will be discrete. Xn is discrete, yn is discrete. So what to do is we will do some processes, some operations with the help of these systems so that the output has some more desirable properties, or output has some information that is needed that was not present in the xn. So a discrete time system, input is xn, that is discrete. It will do some operations on the xn to produce the yn. Again, yn is discrete. For example, simply you time shift the input sequence xn. It is a discrete time system. Simply you square all the samples in input sequence xn. This is your discrete system. In this, what is doing discrete system in first case, it is just doing the time shifting of the input sequence. In second example, it is just doing what? The square of each and every sample of the xn. So this is my discrete system. So what are the types of the discrete systems? First, we will discuss linear and non-linear systems. Discrete system is a linear system if it follows two properties. One is the homogeneity and the second one is additivity. Okay, we will discuss what are these two properties. So first, homogeneity is what? You are giving a sequence xn to the system. Xn is given to this discrete system. Yn is the output. What you get? Now this this input is multiplied by k and given to the same system. You get the output multiplied by k. This system follows the property of the homogeneity. Xn is multiplied by 2. Its output yn is also multiplied by 2. Then it is said to follow the property of the homogeneity. Second property, additivity. You give the x1n to this system, you get y1n. You give x2n to this system, you get y2n. You give the sum of these two inputs to this system, x1 plus x2. If you get the output as y1 plus y2n, the summation of these two outputs, the system is said to follow this property. If it follows both properties, homogeneity as well as the additivity, the system is said to be non-linear. It is said to be linear. If it does not follow these two properties, then the system is said to be non-linear. So mathematically, if x1n is given, we get y1n. If x2n is given, what we get is y2n. If we give x1 plus x2n and we get the y1n plus y2n, then it is said to follow the property of the additivity. This is the one condition. Second condition is you multiply xn by a, the output is multiplied by the same factor. This is the homogeneity. If it follows both like that, you multiply x by a and x2 by b and doing the summation of this and given to this system. The output you get is the output multiplied by a, this output multiplied by v, and the summation of this. So whole of this system is what? Your linear system. It is following the property of homogeneity as well as it is following the property of the additivity. So in one line it can be written as this operation, this transformation on the signal a1 x1n plus a2 x2n gives the output as a1, this operation on the x1n plus a2 multiplied by the operation on the x2n, where x1 and x2 are any arbitrary inputs and a1 and a2 are the constant. So this equation, in this equation, it follows both properties of the linearity, that is the homogeneity and the additivity. If it does not follow any one of these property, even then the system is nonlinear. It is following homogeneity but not following the additivity, system is nonlinear. If it is following the additivity but not following the homogeneity, the system is nonlinear. So next type of the system is time invariant system, or it is also called shift invariant system. Now, you give the xn, you get the yn. You time shift the input by s samples. If the output is also shifted by s samples, the system is said to be time invariant. If it is not shifted by the same number of the samples, the system is said to be time variant. So this is about the time invariance. Mathematically, you give the x1n, you are getting y1n. You give the x1n minus n naught. If you get the output as shifted by the same n naught number of the samples, your system is time invariant. If it is not shifted by the same number of the samples, your system is time variant. So it is written as ynk t x minus n minus k. Input is shifted by the k samples. This is the xn is the input sequence, yn is the output sequence. Xn minus k is the time shifted sequence, yn minus k is the time shifted output sequence. So you can see in this equation, if input is shifted by k samples, the output is also shifted by the k sample, and the system is your time invariant. Static versus dynamic system. Third categorization is static versus dynamic systems. In static system is one in which the output at any instance depends only on the input sequence at that instant, but does not depend upon the past values or the future values of the input sequence. Whereas dynamic system is just opposite of that. The output depends upon the present as well as past or the future inputs. Yn is equals to a into xn. Y0 is x0 multiplied by a. Y1 is x1 multiplied by a. Similarly, y2 is equals to x2 multiplied by a. So the output only depends upon that particular sample of the input sequence. Zeroth output needs only zeroth input sample. First depends upon only the first. So this is your static system. Similarly, if yn is 3xn minus 2, this is a dynamic system. y4 is equals to 3x2. So output at the 4 depends upon x2, that is a previous sample. So this is your dynamic system. In dynamic system, the output can depend upon the present, past or the future inputs. It only depends upon the present input, then this is a static system. Causal and non-causal system. This is another categorization. A system is causal system if the output at any instant depends upon only the present and the past input, but not the future. Yn 2xn, it depends upon only present input. So this system is your causal system. No, non-causal system, see here. This is an example of non-causal system. Y0 is dependent on x2, a future value. Y1 depends upon x3, a future value. So this system depends upon the future values. This is your non-causal system. This system is your causal system. Even if system is 2xn minus 1, even then it is causal. Because in that case also it depends upon the past inputs, not the future. But in this case, it depends upon the future inputs. So this is called the non-causal system. Next categorization is the stable versus unstable system. It is defined by Weibull stability. Weibull stability is bounded input, bounded output. If the input is bounded, then output has to be bounded. Mathematically, if this is your input, it is less than bx, a value, let it be. But bx is less than infinity, means it is bounded for every value of the n. For that particular input, the output has to be bounded. Output has to be less than by, where by is less than infinity. So if we give the bounded input, the output is also bounded, the system is said to be stable. If we give the bounded input, but we are not getting the bounded output, the system is not stable, is unstable. Now, so far we have discussed what is discrete system and what are the different types of the discrete systems, like linear, non-linear, time variant, time invariant, like that. Next we will discuss a very, very important concept of the DSP. That is called, you can say, the foundation of the DSP. That is the synthesis and decomposition. What is synthesis? Process of combination of a signals by scaling followed by the addition. We combine a number of signals x1, x2, x3. Scaling. Scaling means multiplying by them some constants. x1 is multiplied by a1, x2 is multiplied by a2, x3 is multiplied by a3. After these scaling, these are added to give the signal xn. This is known as the synthesis. Just the reverse of that is the decomposition, where a signal is broken into two or more additive components, like this. If we have xn, it is divided, it is decomposed into x1, x2 and x3. This is known as the decomposition. Now, you add 15 plus 35 to give the 40. This is your synthesis. You are adding two components to get a signal. Now, if we want to decompose 40 into some signals, it can be defined in a number of ways. It is fixed, 15 plus 35, that is 40. But 40 can be written as 10 plus 30, 20 plus 20. Sorry, it is 15 plus 35, it is 50. Okay. You got the concept. We add two components to give a output. This is your synthesis. You break a signal, break a number into some smaller numbers. This is called decomposition. This can be written as 10 plus 10 plus 20. Again, it's a decomposition. So, suppose we have a signal xn. It is decomposed into x0, x1 and x2. Suppose this is one signal, this is another signal, this is third signal. Xn is broken into the three signals. That is your decomposition. If you add back all these three components, that is known as a synthesis, you will get the same sequence. You will get the same discrete signal. No. Why it is important? Why decomposition or synthesis or superposition are important? You will see signals are viewed or signal are broken into the some simpler signals. You have a very complex signal. You have to analyze that. It is quite difficult. What you do is you break into the some simple signals, you do the analysis and add back to get the output. That is the main basis of all signal processing techniques. You will see, like convolution, Fourier transform. All these are based on this thing. Breaking a signal into some simple signals. Then doing the analysis on that, again then add up to get the output. Suppose we want to multiply 2441, 2441 by 4. Okay. It puts some load, some stress on your brain. So the simpler ways doing this is to break this signal into some simpler signals, then doing the multiplication and then synthesis, adding up, so that the multiplication becomes easy. See here. In this we have broken 2441 into these four signals. 2000 plus 400 plus 40 plus 1. Then multiplied by 4. This is the decomposition. 2000 multiplied by 4, 400 multiplied by 4, 40 multiplied by 4, 1 multiplied by 4. These multiplications are easy. You can easily multiply 2000 by 4, 400 by 4, 40 by 4, 1 by 4. You get these signals and then you add up all these to get the output. So we are getting the same output by breaking this complex signal, this difficult signal into the first simpler signals. That is the decomposition. Then doing the operations and then doing the reverse of that. That is the synthesis and get the output. So this is the principle of almost all the signal processing techniques. A complex signal is broken into the smaller signals, into the simple signals. Then you do the processing like that. And then you do the synthesis. Then you add up these and to get the output. So first decomposition that we will discuss is impulse. What was an impulse? It has a value of 1 unit impulse. It has a value of 1 at 0th sample and all other samples are 0. Impulse sequence will have a value of non-zero at any one sample and all other samples are 0. So in impulse decomposition, what has been done is n sample signal is broken into the n component signals, each containing n samples. We have 4 sample signal. It will be broken into the 4 components. Each component will have the 4 samples, but with only one non-zero, and other 3 will be 0. As impulse has only one non-zero value and all other samples will be 0. Each component of the signals contains one point from the original signal, with the remainder of the values being 0. We have 4 samples. One component will have one sample, another component will have another sample, third component will have third sample, fourth will have the fourth sample. We will see the example. A single non-zero point in a string of zeros is called impulse, as we have discussed. Now, what is the use of the impulse decomposition? When you have to analyze a signal, what you are analyzing only one sample, only one impulse. All others are 0. Then you take the another sample, analyze it, and then take the another third one, then you take the fourth one, and all outputs are combined together. When knowing how a system responds to an impulse, the output of the system can be computed for any given input. That is the convolution that we will discuss in the later slides. Now see here, you have these samples. 1, 2, 3, 4, 5, 6, something like that. Now, xn, it is broken into the first x0. It has only one sample. All other are 0. This sample. In second sample, in second component, you have this one. This one. All other are 0. Similarly, in the next, you will have this. All other are 0. You are taking one sample at a time. That's why this is known as the impulse decomposition. In 27 sample, you have this value. So, this is a way of combining them. No. You have broken this system into these 3 inputs. 1, 2, and 3. 3 non-zero components, samples it has. So, this is the first sample in the signal x0. All other samples are 0. In x1n, you have this second sample, all others are 0. Similarly, in x2, you have this sample, all others are 0. When you give this input to this system with one sample, this is your output. When you give this input to this system, this is your output. You give this input to this system, this is your output. If the system is linear, only in the case of linear system, you do the sum of all, give to this system, what you get, the sum of all these outputs. This is true only for the linear systems, not for the non-linear systems. So in more emphasis in the DSP will be on the linear systems and time invariant system, that we will see in the later slides. LTI system, that's are called LTI, linear time invariant systems. So you get the output in this way, a very easier way. See, in this is another way of the representation to make it more clear. So this sequence has 4 components, 1, 2, 3, and the 2, with 1 as the 0th sample. So it will be broken into the 4 components. How many components? 4 components. If we have the 4 samples, it will be divided into the 4 components. First has only 1, all other has 0. Second has only 2, all other has 0. Third has 3, all other are 0. Similarly, this is 2, all other are 0. Only one non-zero sample in each of the components. Now, you have this sequence. This is your unit impulse. Unit impulse is what? 1 at 0th sample, all other samples are 0. This is your delta n, first one. So this is what? Delta n shifted by 1 to the right and then multiplied by 2. Delta n minus 1 multiplied by 2. So what this should be? Delta n shifted by 2 and then multiplied by 3. This will be delta n shifted to the left, then multiplied by 2. So this signal xn, any arbitrary signal, is written in the terms of what? Shifted and scaled delta n. Any sequence can be written in the terms of unit impulse. Unit impulse scaled and shifted. Scaled means multiplied by 2, multiplied by 3, multiplied by 2. Shifted, this is delta n minus 1, delta n minus 2, delta n plus 1. So if we generalize this, any arbitrary sequence can be represented as sum of scaled and time shifted unit impulses. Mathematically, it is written as xk delta n minus k. You had the 0th sample, it will be multiplied by the 0th input, that is 1 in this case. If it is shifted by minus 1, k is equals to 1, it will be multiplied by xk. Where is xk in this case is 2. That's why it is multiplied by 2. Similarly, x minus 2, it is x2. x2 in this case is 3. It is multiplied by 3. If k is minus 1, that is n plus 1, then it is multiplied by x minus 1. X minus 1 in this case is 2. That's why it is multiplied by 2. So in general, any arbitrary sequence, not a particular sequence, can be represented as sum of the scaled and time shifted unit impulses. This is a very important property of the discrete sequences, that they can be represented in terms of the impulse decomposition. Now, we will see what is the advantage of this. You give the delta n to an LTI system. Now here it is. I am writing only LTI systems, linear time invariant system. The output you get is Hn. That is known as the impulse response. Impulse response is what? Output of a system when the input is unit impulse, when the input is delta n. So any sequence decomposed into a number of components, you give it to LTI systems, its output will be the unit impulse multiplied by corresponding samples from the input. So it is quite easy. Why it is easy? Because what you should know only is about the Hn. If you know the Hn, you can compute the output of an LTI system due to any of the arbitrary input. You know Hn, you give any input to the LTI system, you can find the output. That is the advantage, that is the main point of the main basis of the analysis of the LTI systems. What you need is only its response corresponding to delta n. That is known as the unit impulse response, that is Hn. You give Xn, you know the Hn, you do some operation that we will see, the convolution. You convolve Xn with Hn to get the output. What you need to know is only Hn. Okay, this is some mathematical treatment of that, although I'm avoiding most of the mathematics. Xn is what? That we have seen. It can be written in terms of what? Delta n multiplied by the corresponding samples in the input. Now, you have some discrete system T on Xn. You transform that Xn to get the Yn. Now put the value of Xn from this equation in this. This is a transformation of this. As xk are constant, if the system is linear, we can take these out. T goes inside. Output corresponding to this multiplied by the scaling factor. That is one of the properties of the linearity. Then added, this is the also property of the linearity. So you get something like that. So transformation of delta n minus k is hnk. Its value at the kth sample. As the system is also time invariance, nk is equal to hn minus k. If the input is shifted by k samples, output is also shifted by the k sample. This is the property of the time invariance. That's why we are taking only LTS system. We have used the linearity, we have used the time invariance. And the output what we get is Yn as k is equals to minus infinity to infinity xk hn minus k. This is the convolution sum. This is known as the convolution equation. A very, very important equation in the DSP, convolution. Its representation is something like that. Xn convolved with the Hn to get the Yn. Next we will see how to compute it. Mathematically you will have to compute it. Computation method. So this is your basic equation. This equation is known as the convolution sum. Yn is equals to k minus infinity to infinity xk h and not k. So what is the first step? You will have the hk, you will fold it. Fold it around the origin to get the h minus k. All the right samples will be reflected to the left and the left will be reflected to the right. It's just something like putting a mirror at the 0th sample. Step 2. Then it will be shifted by n0 samples. Now, whether to right or left, it depends on the value of n. If it is positive, then shift it to the right. If it is negative, then it is shifted to the left to get the hn0 minus k. We get this. So third thing is, it has to be multiplied by this xk. Then xk is multiplied by hn0 minus k to get a sequence that is termed as v and not k. Let it be. That is equals to xk hn0 minus k. Then we do the summation of this sequence to get the output, because here it is the summation. So at n is equals to 1, y1, here it will be 1. At y is equals to 2, here it will be 2. When it is minus 1, here it is minus 1. Here it is minus 2, it is minus 2. In the last step, you sum up all the values of the product sequence, this sequence, to obtain the value at n is equals to n0. To obtain the value at n is equals to 1, at n is equals to 2, n is equals to 3. Similarly, n is equals to minus 1, minus 2, until you get the 0 values. I will take this example to make these steps clear. how to convolve Hn and Xn. Suppose we have an impulse response Hn as 1, 2, 1, minus 1 with 2 as the 0 sample. This is your first sample, this is your second sample, this is your minus 1 sample. Similarly, we have Xn as 1, 2, 3, 1. This is your first sample, 0 sample, this is your first, this is your second, this is your third sample. Now, how to convolve that? First of all, first step, it has to be folded. 1 minus 1 will go to this side, 1 will come to this side. Then you multiply these two. Then you do the summation. It's something like that. Suppose this is your HK. This is your XK. So what will be the first step? We fold HK. Here. It is folded around the 0th sample. Then multiply it by xk. N is equal to 0. No shifting. What you get is this product. What should be the next step? This has to be shifted. You shift it. Again multiply it by the xk. You get this sequence. Similarly, you shift it to h2 minus k, h3 minus k, something like that to get the sequences until you get the 0. Similarly, shifting to the other side, you will have h minus 1 to get the y minus 1, h minus 2 to get the y minus 2, h minus 3 to get the y minus 3. In each and every case, it has to be multiplied by xk. You get this product. In the end, you do the summation of all these. In this, it is 4 plus this plus this. In this, it is 1 plus 0, 0, something like that. When you do the summation, you get the yn. At 0th, this value is 4. At 1, its value is 8. At the 2, its value is 8, and so on. You get the values at the 5th as minus 1, 6, 0, 7, 0, and you need not to compute further. You need not to shift the HK further. Similarly, on the other side, it is shifted by 1, minus 1, it is 1, this is 0, this is 0. You are getting the zeros, you need not to compute any further components. So this is the way to compute the convolution. In thumb rule, if you have 4 components in this and 3 in this, total is 7. The output of the convolution will be 7 minus 1, that is the 6 samples. Then this will be 6 samples. This is just to cross verify your answer, that whether it is right or not. So this is your convolution machine. You have HK, flip it around the 0th, fold it. You give Xn, multiply these corresponding samples, and do the summation. You will get 1 point. Then you shift this towards right or left. Again multiply it with Xn input sequence and do all the summation of this, you get the second point. Then you shift in 1 more point by 1 more sample, do the multiplication. Whatever the sequences get, do the summation. This is your output. You have to keep on doing until you get the zeros. And the thumb rule to check your output is, if it has 4 samples, it has the 4 samples, 4 plus 4, 8, it will have 7. Suppose this is the 5, this has 4 samples, 5 plus 4 is 9, the output will be of the 8 samples. This is just a way to verify your output. So today we have discussed about some basic discrete systems, types of discrete systems, and very important property in the DSP, that is the decomposition and the synthesis. Today we have discussed the impulse decomposition, and based on the impulse decomposition what we have is convolution sum. And the importance of the convolution sum lies in the fact that if you only know the impulse response of a discrete system, you can find the response of that discrete system due to any of the arbitrary inputs. If you know the response of a system due to delta n, that is called as impulse response, you can find its output due to any of the inputs. That's a very big property. So this is all about this lecture today. Thank you very much.